This is Voyager Notes, a transmission from 25 billion kilometers, still transmitting.
On the 19th of October 2016, the Schiaparelli demonstration module entered the Martian atmosphere and fell silent 40 seconds before it was supposed to touch down. That 40-second gap is the story, not the crash itself. The crash took a fraction of a second. What took 12 years of planning and what the ESA Inquiry Board spent months reconstructing was those 40 seconds. A cascade of decisions made by software running faster than any human could intervene, each one logical, each one wrong. The module had been designed to prove a point, not to do science, to land. Schiaparelli was the entry, descent and landing demonstrator module of the ExoMars program, a joint ESA and Roscosmos mission. Its companion, the Trace Gas Orbiter, was the mission's primary scientific payload. Schiaparelli was the proof of concept, the rehearsal. It carried a small meteorological package, but its real function was to survive entry and touch down intact, so that Europe would have demonstrated on the record that it could put hardware on Martian soil. The ExoMars program had been in development for years before the 2016 launch window opened. A Mars landing is among the most constrained engineering problems in planetary science. The atmosphere is thick enough to heat a descending vehicle to hundreds of degrees, but too thin to slow it to a safe landing speed on its own. Every Mars lander since Viking has threaded this same needle: heat shield, parachute, retro rockets in sequence, each transition timed to within fractions of a second. There is no margin for a late correction. The round-trip signal delay between Earth and Mars on the 19th of October 2016 was roughly 9 minutes and 46 seconds. Mission Control could watch. It could not help. Schiaparelli separated from the Trace Gas Orbiter 3 days before entry. From that point, the module was autonomous. It carried an inertial measurement unit, a sensor cluster that tracked orientation and acceleration, and a radar altimeter designed to take over from the IMU once the vehicle was close enough to the ground for radar ranging to be reliable. The handoff between those two systems was a known transition point in the descent sequence. What the team didn't know before the inquiry was what would happen if the IMU produced a reading outside the expected range at exactly the wrong moment. The descent began well. The heat shield performed, the parachute deployed on schedule. Here is where the sequence unraveled. During parachute inflation, the module experienced a rotation, a spin that the inertial measurement unit attempted to track. The spin briefly exceeded the IMU's measurement range. The unit saturated. It reached the edge of what it could record and held that value, feeding the guidance computer a figure that no longer corresponded to what the vehicle was actually doing. The computer, processing that figure, calculated that it was already below ground level. It concluded the landing had occurred. It had not. Schiaparelli was still approximately 1 kilometer above the surface of Meridiani Planum. The sequence that followed was the sequence designed for post-landing. The parachute was released, the retro rockets fired for approximately 3 seconds, then shut off. The computer believed there was nothing left to do. In the logic of the guidance software, the vehicle had touched down. In the reality of Meridiani Planum, Schiaparelli was in free fall from 1 kilometer up. It struck the surface at 540 kilometers per hour. The impact was confirmed by the Mars Reconnaissance Orbiter's context camera, which returned images showing a new dark mark on the plane, consistent with a high-velocity impact and the dispersal of propellant. The ExoMars Inquiry Board, reporting in 2016, traced the failure precisely to the IMU saturation event, a measurement that lasted approximately 1 second, but whose consequence cascaded through every system downstream. Loop hash 1 opened. What exactly did the computer see in that 1 second? The IMU didn't fail in the sense of breaking. It produced a reading. The reading was, by the sensor's own internal logic, valid. The problem was that valid in this case meant the output had hit a hard boundary and stopped changing, a condition the guidance software had not been written to treat as suspect. This is a subtle category of fault. The hardware functioned, the software functioned. The integration of the two produced a result that neither component tested individually would have produced. The inquiry board identified this as a software logic error. The guidance algorithm lacked a check that would have recognized the saturated IMU reading as physically implausible. No one had modeled that specific saturation event during the descent phase in combination with the parachute-induced rotation. The scenario was, in the board's assessment, not anticipated in the pre-flight testing regime. Loop hash 2. There's a harder question underneath that finding. How many other unanticipated combinations existed in the tested envelope? The inquiry board's report addressed this specific failure mode. What it couldn't address, what no post-mortem can address, is the size of the space it didn't look at. Every spacecraft that has ever landed on Mars has threaded its own unique path through a decision tree of thousands of contingencies. Most of those paths were never traveled. Schiaparelli traveled one that hadn't been mapped. The trace gas orbiter, meanwhile, was in good health. It successfully entered Mars orbit on the same day Schiaparelli fell, and it continues to operate. It has returned data on trace gases in the Martian atmosphere, including measurements of methane distribution that remain part of active research. The orbiter was the scientific mission. The lander was the demonstration. The demonstration failed and the science continued, which is one way to read the outcome, though it doesn't resolve what was lost. What was lost, concretely, was the meteorological data the small surface package would have returned. More significantly, what was lost was the confidence that the EDL system was flight-proven. The ExoMars 2022 rover, later renamed and rescheduled, then suspended following geopolitical events in 2022, was intended to use a more sophisticated version of the same landing system architecture. Schiaparelli existed in part to validate that architecture. Its crash left a gap in the validation chain that no amount of modeling fully closes. You can rerun the simulations. You can update the software. You cannot run the test again on Mars in 2016. The dark mark on Meridiani Planum remained. The context camera image shows the impact site clearly, a dispersal pattern consistent with the propellant from the retro rocket system, and a central feature that is the module itself. There's no ambiguity about what happened on the surface. The ambiguity lives in the 40 seconds before impact, specifically in the question of whether the software, given a plausible but erroneous input, did exactly what it was told to do, or whether it did something its designers would not have recognized as intended behavior. The inquiry board's answer was the former. The software followed its logic correctly and the logic was incomplete. That's a harder finding than a broken component. A broken component can be replaced. Loop hash 3 opens here. The IMU saturation scenario is now documented, corrected, accounted for. But the category of fault it represents, a valid reading that is contextually wrong, fed to a system with no mechanism for contextual verification, isn't unique to this mission, this sensor, or this planet. It is the class of failure that lives at the boundary between hardware specification and software assumption. The inquiry board found it. The team corrected it. What remains open is whether the correction addressed only the instance or the class. Paying off loop hash 1. The computer saw in that 1 second a saturated value that its guidance algorithm translated directly into altitude data. It saw ground. It acted on what it saw. The action was irreversible before any human on Earth could receive the telemetry that described it. Paying off loop hash 2, the tested envelope for Schiaparelli's descent did not include the specific combination of parachute-induced rotation magnitude and IMU saturation timing that produced the failure. Whether that combination was improbable or simply unmapped is a question the record doesn't cleanly resolve. The mission control team was watching data from the event with a 10-minute delay. By the time the first indication of anomaly arrived at ESA's operations center, Schiaparelli had already been on the surface for nearly 10 minutes. That is the particular texture of deep space loss. It's not a live emergency, it's a reconstruction. The team sat with the telemetry, read backward from silence, and assembled what happened from the last signals received before the 40-second gap closed. The module transmitted until approximately 1 minute before impact, then it stopped. That final transmission has been analyzed. It contains no indication that Schiaparelli knew anything was wrong. The guidance computer, in its last recorded state, believed it had landed. We still don't know if Europe will land on Mars. The path that runs from Schiaparelli's wreckage on Meridiani Planum to a functioning ESA rover on the Martian surface has been interrupted, extended, and redrawn more than once. The 40 seconds of silence on the 19th of October 2016 are documented and explained. What the explanation hasn't answered is whether the next descent sequence, when it finally flies, contains a gap in its own tested envelope that nobody has mapped yet. The signal from Schiaparelli stopped 40 seconds before it should have reached the ground. Which detail in that reconstruction stays with you?
This was Voyager Notes. The signal is still coming back.